Hey everybody, this is a presentation that is going to help you understand a little bit better about what is an acid and what is a base. Now, I know you guys know from past science classes and other life experiences that some things can be classified as an acid, some can be classified as a base, and they have certain properties that go with them. I know that you're familiar with like pH scale. People might have hot tubs or pools or fish tanks and have measured a pH scale. A lot of times people are familiar with indicators like a piece of litmus paper, or you've seen me use phenolphthalein before to add it to a solution, and judging by the color, we can classify it as an acid or as a base. But what we really want to do today with this presentation is really define what is an acid and how do the acids act in chemical reactions, and what is a base and how do bases act in chemical reactions. And it all really boils down to the ionization of water. Now, I know water is a molecular substance, so that probably sounds really funny to say that it ionizes. If you have two water molecules, and you can see here that, we have two water molecules on the reactant side of this double arrow. Remember that they are highly polar, and if they hit each other just right, a hydrogen can transfer from the one water molecule to the other one, creating these two ions. Now, this is a reversible reaction. You see that by the, by the double arrow here, which means that, these two ions can bump into each other and turn back into the molecule. And being a reversible reaction, we can write an equilibrium expression for it, and it has a really small K value. Remember that if something has a really small K value, that means that the product side has really small, tiny values. The K value for this reversible reaction is 1 times 10 to the negative 14th, which that's going to play into the pH scale. That negative 14, the pH scale is out of 14. We'll learn about that next week. But so there's not very many of these ions in relationship to the amount of water molecules that would be in any sample of water. But what this tells us is that every single sample of water has a few of each of these ions in it. Now, I know the OH minus 1 you're familiar with, that's hydroxide. The H3O plus 1, they call that the hydronium ion. That is actually a water molecule that has a hydrogen ion stuck to the negative end of the dipole. And so they call that hydronium. Honestly, you can take a water out of each side, take a water out over here, take this water out, and have this, which is more like a net equation of what is going on. One of the water molecules is going to break apart to make H plus 1 and OH minus 1. And every water solution has both of these ions. Now, H plus 1 ions, when they are present, that is what gives something the properties of an acid. OH minus 1 ions, when they are present, that is what gives something the properties of a base. But if you have them in equal amounts, like when a water molecule breaks apart, for every hydrogen, there's a hydroxide, then that solution is going to be neutral. Now, you can add things to water that could interfere with this equilibrium. We learned about Le Chatelier's principle in the last unit. Like, let's say, for example, I dissolve some sodium hydroxide in here. So, oh boy, there we go again with the eraser. Okay. So if I dissolve some sodium hydroxide in my solution, that's going to add sodium ions and hydroxide ions to this mixture that already has water molecules, hydrogen ions, hydroxide ions. So the result is, remember when we looked at Le Chatelier's principle, that would increase the number of hydroxide ions, and we learned that the reaction would shift to the left. It'll shift to the left and bring both of them back down until, the hydrogen times the hydroxide is back to equaling 1 times 10 to the negative 14. It'll reestablish that equilibrium. Now, the sodium ion has no effect. Why does it have no effect? It's not part of this reaction. Remember when we did Le Chatelier's principle? If there's something in there that, is not part of the equilibrium, it's not going to have an effect if you add it to the mixture. But the net result is that once the new equilibrium is reestablished, we've got more hydroxide now than hydrogen in this mix because of adding sodium hydroxide. We've now got a base. When you've got more hydroxide than hydrogen, that solution is going to behave like a base. And, then the reverse can happen. You can add something to your solution that will increase, the amount of the hydrogen. For example, I could dissolve molecular HCl. Molecular HCl is just H-Cl. It's a gas, actually. And as a gas, when the hydrogen is bonded to the chlorine, it doesn't act like an acid. I'll tell you a story about that then when we talk about it here in future times. But when it's dissolved in water and it breaks apart, it's going to add hydrogen ions and chloride ions to my solution. Now, chloride is not a part of the equilibrium, so we can ignore it. But the hydrogen ions, that increases this. It shifts, the equilibrium shifts to the left to bring the hydrogen back down and the hydroxide down until, the new product of hydrogen times hydroxide is once again 1 times 10 to the negative 14. And once that new equilibrium is established, we're going to have more hydrogen than hydroxide. This solution is going to act like an acid. So, you can have situations where you add something and it doesn't interfere with this. Like, for example, what if I add salt? That does not show up. Hold on. What if I add some salt? Like, some sodium ions, some chloride ions. Guess what? They dissolve in the water. They don't affect this equilibrium. The ratio of hydrogen to hydroxide remains equal, and it's neutral. But if you add something that interferes with this equilibrium and changes the ratio of hydrogen to hydroxide, you could end up with an acid if your hydrogen is greater than your, if it's greater than your hydroxide. So if hydrogen is greater than the hydroxide, that's going to be an acid. If you add something to the solution that makes hydroxide greater than the hydrogen, that's going to be a base. But if you add something to water and create a solution where it doesn't affect them and they remain equal, then that's going to be a neutral solution. All water-based solutions have the potential ability to become an acid, a base, or be neutral. It is very simply the ratio of hydrogen to hydroxide in that water-based solution that determines if it acts like an acid, a base, or if it's neutral. It's all about the relative ratio of those ions. Now, Arrhenius recognized this. Let me hide this so we can see this a little better. Arrhenius recognized this in the 1800s. Svante Arrhenius was a Swedish chemist. He recognized that if you add something to a solution and you get hydrogen ions in that solution, that is going to give you more hydrogens than hydroxides, and that's going to act like an acid. Here's where I wanted to tell the story from college. We once had some HCl gas that was invented properly in organic lab, and it got into the room, and The only way that we knew it was in the room and in the atmosphere in the room was that our eyes, noses, mouths, lips, anything that was moist started to itch and bother us. Because as a gas, this hydrogen is bonded to the chlorine and it's not going to behave like an acid. But as soon as it dissolves in water and the hydrogen ion is released and becomes H plus 1 instead of being bound up to the chlorine, then it's going to act like an acid. And so we could tell because the moisture in our eyes, our nose, our mouths, those places, were dissolving the HCl gas, breaking it apart, and then we were starting to feel the effects of that hydrogen ion. Our eyes were itching, etc. So, like, had someone had wet hair, then it might have dissolved and started to make their scalp itch, etc. So anything, it's not just when hydrogen is present, and it's anything that dissolves in water and produces hydrogen ions in the solution. You have to have hydrogen ions in the solution for it to behave like an acid. A base then would be anything that, contains hydroxide, and when you put it in water, it breaks apart and it adds hydroxide ions to the solution. And that's going to be then something that's going to behave like a base. So, chemists are now starting to be able to identify acids and bases, or what should act like an acid or a base, just by looking at their chemical formula to see what they contain, what they're going to break apart into. And then they find things like this, like, for example, ammonia, NH3. That's a gas. And when it dissolves in water, it acts like a base. And yet there's no hydroxide in there anywhere. They come across other things like baking soda, sodium bicarbonate. That's this. It's a solid. You know what baking soda is. You dissolve it in water, it's going to act like a base. And there's no hydroxide in that formula anywhere. So they start to realize that there are compounds out there that their solutions do possess the properties of an acid or of a base, yet they don't have hydrogen ions or hydroxide ions in them. So they have to start to figure out what's going on. Two different scientists kind of figured this out around the same time. Johann Bronsted and Thomas Lowry. They actually didn't work together. They never even really met from the way I understand it. But history has credited it to both of them because they both kind of came up with this theory at around the same time, that we don't need to wipe out the definition of an arrhenius acid and an arrhenius base. I mean, that makes it really easy to identify an acid or a base. If something has H plus 1 ions, it's going to act like an acid. If something has OH minus 1 ions, it's going to act like a base. But we needed to add to that definition and include compounds that behave in these ways right here. An acid is something that will donate an H plus 1 as it reacts. And a base is something that will accept an H plus 1 throughout the course of the reaction as it reacts. So you have to look at the overall reaction and see how the molecule or, particle reacts. Like, for example, if you look here at this, and then you look at it on the other side over here, you can see that it lost an H. It lost the H that was in the front. When it lost the H, its charge went down by 1 because H has a plus 1. So we had to take a proton away too. So it's down the -1 instead of being neutral. That means that this compound right here was acting as a Bronsted-Lowry acid, or I'm going to label it as a BLA, a Bronsted-Lowry acid. It is donating an H in the course of this reaction. Then you look at the water, the H2O, and you see that it turns into H3O plus 1. It accepted the H. That makes the water a Bronsted-Lowry base. Now, I know that's a little uncomfortable, thinking about water as a base. We'll talk about that in a minute, a little bit more. But in this particular reaction, the water is a Bronsted-Lowry base because it accepted the H. When it accepted the H, its charge will go up by 1. So that's how it got the positive 1 charge over here on the other side. We can see that. And we can see that in this reaction, we have an acid and we have a base. One compound acts like the acid and gives away the H. The other one acts like the base and accepts the H. It does, in fact, increase the number of hydronium ions in the solution, which makes sense. Then the solution will test acidic and have the properties of an acid because now it's got hydronium ions in there. And also, we can look at the reverse reaction, and we can see that in reverse, the H3O gives away an H to turn back into water. So we will call the H3O the conjugate acid. So Ca stands for conjugate, and you'll see that in the reading, acid. And Cb stands for conjugate base. Every Bronsted-Lowry base has a conjugate acid. In reverse, it's behaving like an acid. Every Bronsted-Lowry acid has a conjugate, has a conjugate base because in reverse, it's going to accept an H when it turns back into the original. And remember, it's a reversible reaction. So the Bronsted-Lowry model was more for partial ionization, where you have some molecules and some ions. All of these reactions are going to be reversible, whereas it turned out that Arrhenius model was more compounds that when you added them to water, they completely just broke apart into positive and negative ions. They just ionized. And if you look on that previous slide, you can see they were, one-way arrows. So they were not reversible reactions. So every Bronsted-Lowry acid has a conjugate base. Every Bronsted-Lowry base has a conjugate acid. If the base is kind of weak, then its conjugate acid is really strong. Water is a super weak base, and so its conjugate acid is really strong. Now, the acetate ion and the acetic acid, they're both like kind of moderate, as far as acid base. But look at the next reaction. We can, continue on and label. We got to look at what happens. You see how the NH3 picks up an H when it goes over here? That makes it the Bronsted-Lowry base because it accepted an H and its charge went up by 1. Do you see how the water is giving away an H and turning into that? That makes it a Bronsted-Lowry acid in this case. I know that's kind of weird. Look, here water's an acid. In our previous example, it was a base. Again, we'll talk about that in a minute. But do you see how water, when it gave away an H, its charge went down by 1? And the acid turned into the conjugate base, and the base turned into the conjugate acid. In the reverse reaction, the NH4 is going to act like an acid and give away an H. In the reverse reaction, the OH is going to pick up an H. If it accepts an H, it's acting like a base. And look, this is a really strong base. In the conjugate pair, if OH is a really strong base, that means water was a weak acid. Water can act like a weak acid or a weak base. And that gives water some special properties. It's a substance that can act as an acid or a base. And we call that amphoteric. It's not the only substance. You'll see some other examples of it. Usually it has to be a molecule that either has like a lone pair of electrons, so it can attract an H, like, somewhere like a pair of electrons, or it has a negative charge, so it can attract an H. And then the other thing, it also usually has to also have an H to give. so that it can give away an H. So not everything can be amphoteric, but water certainly can. And how it behaves, like it's a really weak acid. It's a really weak base. If you put it with something acidic, it'll be 4-stack like a base. If you put it with something basic, it'll be 4-stack like an acid. It's kind of just one of those things. It's relative to, what it is paired with. So one of the things that you will have to, one of the skills you will have to have, and when you, look at, when you look at the WebAssign and you look at the worksheet that goes with this lesson, you will sometimes be asked to figure out what's the formula of the conjugate acid or, of the conjugate base for a certain compound. Like, here's an example question. It says, determine the conjugate base of H3PO4. So if it's going to have a conjugate base, that means the H3PO4 is acting like an acid. What do acids do? They give away an H, which means their charge will go down by 1. So basically, take one of the H's away. So you only have 2. And the charge is going to go down by 1 instead of 0. It's going to be -1. You probably recognize this as an ion off of your ion chart. See, you should get things that you recognize or that look, how do you want to say, realistic or possible when you are doing these problems on the worksheets and in WebAssign. Here's another example question. Determine the conjugate acid of Br-1. Now, if we're looking for the conjugate acid, that means the Br-1 is acting like a base. What do bases do? They accept an H. So add an H to the formula, and the charge will go up by 1. Instead of -1, it's 0. Well, this looks familiar too. That's hydrobromic acid. So you'll be doing a lot of those. You'll practice some on a worksheet. You'll also get to practice some in WebAssign. But feel free to look back at this to help you out with those. These are properties of acids and bases. Hopefully we have time to do this lab. If not, I think a lot of this is some things that you're just familiar with from life. For example, like some acids like citric acid, ascorbic acid. Ascorbic acid is vitamin C. Did you ever chew a vitamin C pill? Woo, really sour. If you look at Sour Patch Kids, they are coated with citric acid on the outside. That's the sour, okay? A lot of citrus fruit like lemons are really sour. The only reason that oranges aren't sour, because they do have some acid in them, is they also have a lot of sugar in them to help make them sweeter. That's why lemonade, even though lemons are actually sour, lemonade, we add a ton of sugar to override that sour flavor. Bases, on the other hand, are going to taste bitter. Something like, do you ever have baker's chocolate? Or like the really dark, really dark chocolate, like not just special dark chocolate from Hershey's, but like a square of like 70 or 90% cacao. Chocolate is a base, and it's really bitter. Now, we love chocolate because, again, to combat the bitter, we add a bunch of, sugar and milk and other products to make milk chocolate, and that's, what helps to make it really good. But other things like coffee is really bitter. So some people like that bitter taste. Other people like to add a lot of sugar and cream. If you've ever gotten soap in your mouth, soap is a base, very bitter. Okay. So some other properties, bases tend to feel very slippery. So, the soap, Clorox is a base, very slippery. Litmus paper. There's 2 different colors of litmus paper. There's blue and red. Both of them will end up red in the presence of an acid, and both of them will end up blue in the presence of a base. So if blue paper stays blue, you also need to put a piece of red paper in and see if it turns blue. If red paper stays red, you also need to put a piece of blue paper in and see if it turns red. Because if you have a solution that's neutral, the blue will stay blue and the red will stay red, and like they won't both change. Solutions are conductors. I demonstrated that the other day in class. Acids will neutralize bases, and bases will neutralize acids. So what they do is they equal out and affect that equilibrium that we started with on the first slide, and we'll talk about that a little bit. And then another indicator that you've seen me use this year, phenolphthalein. It's a solution. We'll be using that in the one lab that we're going to do. And phenolphthalein always turns pink in the presence of a base. I'm going to have the chemical reaction on a worksheet that you're going to do. And you'll see that when you add an acid, it makes the reaction shift to make clear ions. And then when you add a base, it makes the reaction shift to make more of the pink ion. And so that's why it turns pink in the presence of a base. These are just some reactions of acids that are really common. And we'll be going over reactions of acids and bases in the second PowerPoint for this unit. But that's an introduction of acids and bases. I hope that, it works for you to look back at this presentation, helps you figure out, is something an acid, is something a base, and I gotta figure out how I can stop this show. There it is. All right, I'm getting a little better at this. But hopefully looking back at that presentation will help you out with what is the definition of an acid, what's the definition of a base, and you can apply that to some of the problems that you're going to solve on worksheets and on WebAssign. Good luck.